We got it to work.
Oh
We finally got it to work. Live. Welcome back to another one of these episodes where two humans decide to have a conversation about science, just science stuff in general. Hope my audio's okay. New mixer, who dis, new mixer. So hopefully my audio's okay. I'm sure I'll get the yay or nay that the audio is working. But at any rate, I appreciate you guys jumping on. Thanks for being patient with this. I think I found out that Richard is trying to shorten these podcasts by having audio issues every show. That takes about 15 minutes to to figure out. I wonder what it is.
I have no idea.
Yeah,
I
should
try to dedicate time to it, and it's like it just doesn't work. I'm
doesn't,
not technically savvy.
which is not a good thing since you work in IT.
Correct. Everything is by luck.
Yeah, but again, I appreciate you guys coming on. Thanks for signing up or sharing videos, previous videos. I appreciate that. Today's episode, if you're reading the title, we're going to spend some time talking about whether or not space time is fundamental, meaning it's the core, meaning that's the bottom, meaning that's the basis. I mean, it's the foundation upon which we build upon. So we'll be talking about that, and I'm sure we'll be talking about some other stuff as well. But I do want to, as usual, have a conversation about fact checking last week's podcast. Yeah, when it's appropriate, I like to spend some time fact checking the information we went over last week, and I don't think we need to fact check a ton. I think what we actually need to get better at, and it would actually reduce a lot of fact checking, is basically explaining that most everything we're talking about is probably just hypotheses. It's just a hypothesis. It's not always agreed upon. It's not always what everyone is saying. So, like last week, we spent some time talking about how our brain is a prediction machine, and how it operates, not so much like a camera, but it uses all of its senses to kind of predict what's going to happen in the future based off of previous patterns. And we made some references to a few folks and a few journals, and that's their interpretation of what's going on. Some of it is accepted, widely accepted, and other stuff is not widely accepted. Some of the stuff is still being contested. So I think that's the part where we probably need to. I think if we just did that, um, most of the fact checking kind of goes away. But I think if you've been following this, you kind of understand what we're doing here. We're two weirdos that can't even figure out audio on a podcast, uh, talking about science as best as we know it. As best as we know, I'm not a doctor in any of this stuff. You're not a doctor in any of this stuff. You've got some schooling in electrical engineering, but I think this is important to have this conversation every single time we do one of these episodes, so people know where we're coming from. Once we have 1 million subscribers, and I don't think we need to explain it anymore. But right now, with the amount of humans that listen to us, we probably need to explain this every single time.
Yeah.
That said, fact checks from last week. Anything you want to add from last week?
Well, I don't really have the transcript from last week, but I know we were talking about the prediction model basically. What it is just wanted to reiterate how the human brain works is it's basically making predictions based on those past patterns, and recognizing additional patterns, and then it uses those senses to correct its predictions. Um, and so, yeah, in real time, it's actually correcting the predictions. It doesn't necessarily. The only time it actually corrects the predictions is when it's wrong. So if it's right, then I mean, the thing is, you would never really know whether or not it's correcting.
Yeah, that's the fascinating thing about it. It's fucking crazy.
Hmm.
If you didn't watch that episode, I highly encourage you guys to go watch that episode. Chime in on that stuff. Add your knowledge to that. Any resources that you may have to that as well. But today I want to talk about, or Richard wants to talk about, and that's kind of the pattern. Is Richard comes up with these most of the time. Um, and this time you want to have a conversation about, is space time fundamental?
Yep.
Well,
So,
oh,
yeah, I mean, basically, that's the question is whether or not it's fundamental. In modern physics, space time is treated as a stage, basically your stage of reality, and that's there's nothing wrong with it. Everything happens somewhere. Every event is going to happen sometime. So, and Einstein unified space and time into a single object, which is space time. So, gravity became a curvature of that entire geometry. So that's been successful so far. That's where you get black holes from. It's where you're getting gravitational lensing. You're getting time dilation. Everything comes from the the idea of space time. That's where you're getting gravitational waves as well. All this has been confirmed. Um, so this is more theory. We're jumping into theoretical physics, that it might not be fundamental, um, may not be the stage, and it may be something else that emerges kind of deeper. So,
yeah. It's for someone like myself who is a big Einstein fan. Obviously, I never want any of his shit to be discredited, but obviously, in the interest of human advancement for however long we've got left on this planet, on this in this universe, it in order for us to move forward, we have to kind of get all of the answers. And this one's a fascinating one to think that everything, because everything is basically, well, not everything, but a big part of physics, especially cosmology, astrophysics, and just the way we understand how matter and time and space and basically everything we're doing right now works, is based off of what Einstein has done. And it's been tested for slightly, what, just a little over 100 years now. um and every single time they test it, it's proven even further. It's very rarely disproved. So when you have something that says, it's not that he's wrong, it's not the foundation, right? We're not saying he's incorrect, or the science isn't saying he's incorrect. It's just saying it's not the foundation. And I think we currently believe, or we understand it to be the foundation on which a lot of stuff is built upon.
mhm.
So that one is weird. So then, what resources? Obviously, I've got my notes, and but I want to see what resources you've got, what you've found. What are we talking about, and what do I need to Google real time as we're having these conversations?
Well, let me first define what I mean by fundamental. Fundamental in physics basically means not made of anything more basic. That's all it is.
Yeah,
Um,
it's the
so
bottom. It's the bottom, and everything else is built upon that, right?
correct.
Yeah, it
So,
is quite literally the foundation
mhm.
on which everything else rests.
Yeah. So, for an example, like temperature is not fundamental. It's actually based off of molecular motion.
Correct.
So, yeah, so that's how it's defined in physics. Pressure, not fundamental. It comes from particle collisions. We did a show about that.
Yeah.
um, Solidity, also not fundamental, comes from electromagnetic interactions. And so, all the properties that we experience are kind of like just a collective behavior of much simpler rules than what we're
Correct.
given.
Yeah.
Um, so modern physics is asking whether space-time itself is more like temperature than like an atom.
Correct.
That's basically what we're doing here. Um, so you have a conflict, of course, between relativity and quantum mechanics, and this is where you and I kind of see different views here.
Correct.
Um, so with relativity, space time is smooth and continuous. Geometry determines motion. Gravity equals curvature, right?
Yeah, I mean, for the most part, that's if we were to take the oversimplified version of it, yeah, that's basically the
Okay.
way it works.
All right. And the difference is in quantum mechanics, reality is discrete. There's probabilities. It's based on relationships between states.
Correct. We talked about entanglement. That's a big part where they're saying that entanglement is
Mhm.
potentially more of a foundation than space time.
Correct.
Yeah.
Um, so some of the two most successful theories in physics, they basically disagree about what reality is made of. That's what we're getting down to. So relativity agrees on one side, and then you have quantum mechanics that believes on, I mean, that agrees on another side, and both of them disagree on reality. So,
So the
um,
what papers do you have or humans that have been working on this? I've got some humans. I'm sure we know both of the or some of them, but I just want to make sure that we don't
well,
get
you have Bell's inequality violations.
vowels,
Bell's theorem.
vowels,
Yeah.
Bell,
Yep.
inequality,
ELL apostrophe S.
inequality, Bell's inequality. Okay, let me kind of get this over here, and then that way humans can see. Let me share this for the humans that do share. All right, Bell's theorem is a term encompassing a number of closely related results in physics, which determine the quantum mechanics is incompatible with local hidden variable theories. Given some basic assumptions about the nature of measurements, the first such result was introduced by John Stuart Bell in 1964, building upon the Einstein's Podesky-Rosen paradox, which had called attention to the phenomenon of quantum entanglement. So it's kind of a small little snippet about it. Let me see if there's any images about this. Um, that's an interesting. The weather is sunny. Alice goes out. Bob goes out. What a weird, what a weird. Uh,
Watch what you Google.
but that is talking about the meaning of Bell's inequality, the mysterious. This is coming from. I don't even know where that's coming from. I don't know what website that is. So we're gonna
So,
say it's not real.
yeah, to define local realism,
Yeah.
it's basically the idea that physical properties exist before we measure 'em. And influences can't travel faster than light.
Uh,
So these experiments are testing Bell's inequalities, or testing Bell's inequalities show that nature does not fully obey local realism.
when we're talking about local realism, it's within your own area. I mean, we know what local means, but I think it's important for us to understand what it means in. in the physics world. So let's
Yeah.
look at
And Wikipedia is saying that in the context of Bell's theorem, local refers to the principle of locality, the idea that a particle can only be influenced by its immediate surroundings, and that interactions. Uh, yeah,
yeah. The
okay,
principle of locality states that objects are only influenced by their immediate surroundings, with information traveling no faster than light. Cool.
correct.
Cool, cool, cool. So, yeah, this is where I start to get confused.
All right. Um, so basically, both theorems are correct. I mean, relativity is correct. Um, Quantum mechanics is correct, but something has to unify them. And so that's when you start to bring in entanglement. It kind of changes the idea of distance. Um, so the quantum entanglement, basically two particles can share a single combined state. Um, Measuring one instantly determines the other. So
Okay.
it's not necessarily communication that's faster than light, but the correlations are stronger than what classical physics allows.
Okay.
Um, so I think I wrote something about it where they were able to successfully measure the speed of quantum entanglement, and I cannot remember for anything. It's in my article somewhere. I wrote it down, and it's not on this new computer, so I can't. I cannot remember it. But it's an extremely small number, in terms of time, and um, it was able to be measured, but it's they're trying to determine whether or not it is faster than light, and they have determined that it's not. It still does not break the speed of light.
And and that's the biggest argument is the speed of light. I mean, I would imagine there's more.
Yeah, basically, they're trying to. The way that quantum entanglement was viewed before is because you have two particles. It can be separated by distance. Distance doesn't necessarily matter, but they behave as one system. So one effect on one has an immediate effect on the other. What they were trying to do is to measure the time that it takes for one to have the effect on the other, and whether or not it breaks the speed of light. What they found is that there is a time difference between one particle being affected by the other, and so once they were able to measure it, they realized that it can't break speed of light because they were able to measure it.
Yeah. But this is, I think, where all of this new stuff starts to break down is, and again, a lot of this is we just don't know yet. We don't have maybe the technology to do, which is crazy to think about in 2026. Like
Yeah.
it is absolutely mind-boggling to believe that in 2026, and I understand I'm looking at this from a human who's using technology in 2026. But like if you look at our technology is so advanced. And again, all we have to compare it to is from 100 years ago, 200 years ago. So like for us, this is incredible. I'm sure when they landed on the moon, the Apollo project, so like they were fascinated on how advanced their technology was at the very moment. So for me, it's mind-boggling to believe we don't have the technology, but that is part of it. Is we just don't have the technology to really measure all of this stuff.
Next episode, are humans getting dumber?
That's I don't fully disagree with that statement, because we rely more and more on the technology. We
Yeah.
lose our ability to use old information because we just don't use it. We just don't use it. There's no need to new technology. But I think that there's this weird place where we're at, where all of these hypotheses cannot be proven, and everything that supports space-time being fundamental has been proven time and time again. Like it's been around for quite some time. Um,
Yep.
and
So I
there's
dropped something in your chat. Juan Molesina's
oh,
ADS CFT correspondence. Want to look that up as well.
so ADS CFT correspondence. So CFT, if I'm not mistaken, let me see. I came across this uh, conformal field theory. Conformal field theory is a type of quantum field theory with extra symmetry. It stays the same under conformal transformation, preserving scaling. Conformal field theory is a quantum field theory with no preferred length scale. Looks the same if you zoom in or zoom out. So if you scale distance, physics doesn't change. That's a big deal in theoretical physics. But it see, and this is where for me it's just like, but it does change. And
Mhm.
the fact that and a simple, and I may be wrong, I may be correlating two different things that shouldn't be mixed in together, but we see this in classical Newtonian physics, which at a scale locally, if it worked, it works amazingly, and it still works. But at a larger scale, it starts to break down. So, like, if again, Mercury, we couldn't figure that out, and that's because Newtonian physics didn't really know about space time, didn't know about um, the fabric of space time and how it bends and it curves, and so it worked, but it needed to be further developed, Newtonian physics. And I again, I may be wrong because again, I'm the dumbass here, but from my very little knowledge of this, it doesn't compute because if I zoom in, zoom out, there is going to be a difference, and we see that in black holes, we see that in atoms, and we see those in neutrons, and there is a difference.
Right. Yeah. So basically, what I'm seeing is you have an entire gravitational universe.
Yeah,
In higher dimensions, is basically equivalent or mathematically equivalent to, say, a quantum field theory in fewer dimensions. So it's the same physics, but different descriptions.
correct. And the ADS, what is ADS? And it's capital S, but what is that? Because this is what you.
Um,
I did see the name
it's
Juan.
anti de Sitter
Okay,
slash conformal field theory.
let's see, anti. So there must be a regular just sitter,
Yeah.
anti de sitter.
Hmm.
Let me see if I Google the. Do, do, do. Yep. So here we go. Let me put this up for again for the humans. Let me share this so that we're all kind of on the same page here. I was afraid I wasn't going to spell it correctly, but here we go. Anti-de Sitter. So anti-de Sitter ADS space is a highly symmetric, negatively curved space-time hyperbolic geometry representing a solution to Einstein's field equation with a negative cosmological constant, often visualized as a saddle shape or a. Oh, this is where we get the Pringles from. Uh,
Yeah.
this is where we get Pringles from. Yeah, yeah, I think that's where we get the fucking Pringles from, if I'm not mistaken. That shape. Anyways, it's weird if that is correlated. Uh, so anti-de Sitter. Let me see something really quick. Versus sitter. De-sitter versus anti-de-sitter. So I want to understand this a little bit more. De-sitter and anti-de-sitter space are maximal symmetry solutions to Einstein's field equation with a non-zero cosmological constant. The core difference is that DS has positive curvature. Okay, so one is just positive, the other one's negative curvature.
Yeah.
Got it. And these
And
are all working on Einstein's field equation.
correct.
Perfect. Got it.
So yeah, there's a duality. Okay. Um, now look up Leonard Susskind, Susskind, and that's
Say that again.
Leonard
Leonard.
Sus. Yeah, Susskind, Susskind.
Yep, he popped up.
This is about the ER and EPR conjecture.
So what is that?
Um, oops, there we go.
He's old, super old.
Yeah, not young at all. So the ER and EPR conjecture is the Einstein-Rosen versus the Einstein-Podolsky-Rosen entanglement.
Got it. Got it.
It's about wormholes, pretty much.
So he's one of the humans that's pro
String
space
theory.
time stuff fundamental.
Yeah.
Yeah, got it. And
So
his whole
he
which one?
he's suggesting that entangled particles are connected by microscopic geometric relationships.
What was his the one that you said before?
Was that the string theory?
Yeah.
Or the one I said before was Juan
It was
Maldacena?
Leonard Susskind, but you
Yes.
said something that you gave me some letters after that.
Oh, ER and EPR conjecture.
Oh,
So ER is just Einstein-Rosen bridge, which is wormholes. And then the EPR is Einstein-Podolsky-Rosen entanglement.
got it. ER equals EPR is a conjecture in physics stating that two entangled particles, as so-called Einstein's Podolsky-Rosen or EPR pair, are connected by a wormhole or Einstein-Rosen bridge, and is thought by some to be a basis for unifying general relativity and quantum mechanics into theory of everything. And that's what they've been looking for a while, how the theory of everything.
Yep.
Doing a movie about that, if I'm not mistaken. I don't know if it's actually about that, but
Hmm.
fascinating.
Yeah. So this is basically saying that space time might be a map of relationships. It again jumps into string theory that everything is connected by microscopic strings. So,
Yeah. Well,
so if that's true, that means that everything's network based, right?
but but I think we already kind of know that, don't we? Or like,
I
what do you
mean,
mean by network based?
like
It's
everything's connected by a string, just like you would a standard computer network or something.
this is where I think these weird hypotheses kind of lose me
Hmm.
because they take something that we've proven and then they just say, well, see, this is also real because this is real, and like they make a leap. And I for me, looking at everything that I've looked at right so far, is I could get to a point where we say space time isn't fundamental, but the leap here is string theory is real because everything's a network. Yeah, but we kind of know that because everything does work together. The sun is the reason we operate the way we operate, but also Jupiter is the reason we operate the way we operate, and Venus affects the way, to a certain degree, to a minimal, but to a certain degree, the way we operate. So I think
Yeah.
we do understand that it is all a network. But for me, anyways, it's a reach to believe that it's also why everything else is real.
Yeah. So they're seeing things as like a good analogy would be internet topology rather than geographic distance. So say you have two different servers, they can be physically apart but still very strongly connected, or they can be physically close and very weakly connected depending on the topology. So that connectivity is what defines a structure between the two servers or in this case, two particles, um, not necessarily a location. So, quantum gravity basically approaches it like spin networks, tensor networks, quantum graphs.
Yeah.
Geometry appears when the relationships are kind of interact. Um, so that's quantum mechanics, or the basically quantum physics. Space may be what relationships look like at large scales. That's what um, most of the scientists are concluding under quantum mechanics. So they just
But
zoom out.
again, I think that that's where it gets to me anyways, where it's you can't have it both ways.
Right.
You can't say this is the way it looks like at this scale, and this is what it looks like at this scale, and then have somebody who supports the fact that or the idea that space-time isn't fundamental, say that it's the same shit whether you zoom in or zoom out. So, like, it for me and again, I'm probably missing something. I'm probably not understanding this, like, somebody probably needs to sit me down and feed it to me like a three-year-old so I can maybe understand this a little bit better. So I fully accept that I'm probably just not understanding this. The the obvious, against this idea that space-time isn't fundamental is slightly over 100 years of evidence.
Hmm.
Like, Einstein has the biggest support and the biggest backing, and that is, if I'm not wrong, hundreds of experiments that try to disprove Einstein, and it all fails. If anything, it all proves it correct, right? So we talked about that one, the gravitational waves one, LIGO, LIGO.
Yep.
I forget what that stands for. Black hole imaging is an Einstein thing. Uh, Gravitational time dilation. Yeah, that's the way GPSs work. GPSs rely on that.
Hmm.
Um, the again Mercury, the way it orbits around the sun, the gravitational lensing, the way light bends. Like, so, we have so much evidence, and it all goes back to the way Einstein explains the way gravity works. Now we understood, and I think Einstein understood there's a limit to this. Somebody needs to add to this. He was trying to, he just never got around to it. He ran out of time chasing his cousins. But everybody else is chasing skirts. Is like, my cousins are the skirts. Uh, so so he got caught up in some other stuff. So I think he understood that there was a limit, but I don't think it would still be building on Einstein. And I think that's the other thing we see here. If I'm not
Hmm.
mistaken, that last two that you just had me look up, even his thing was building on top of, because it was Einstein, Rosen, and it was Einstein, and then the other three, whatever those were, it was still building on Einstein,
Correct.
which makes it fundamental. So
So,
I may be wrong, but go for it.
yeah, of course, with the whole thing, why it really matters. I mean, you have black holes, information stored on surfaces. Um, that's where I start to reference the Bekenstein Hawking entropy. Um,
We're talking about Hawking radiation, right? Or
Hawking radiation versus Bekenstein, Jacob Bekenstein.
'cause that's
So
the
that
real discoverer of the radiation,
correct. Yeah.
which is fucking annoying that pervert, and not even a good pervert, fucking, wheelchair guy, what the fuck's his name?
Stephen Hawking.
Yeah, Epstein Island guy is is credited for that, but he again, go look this up. He was trying to disprove
Hmm.
Bekenstein, is that his last name?
Yeah, Bekenstein is he basically said that black holes should have an entropy proportional to the area of the event horizon. And Hawking came in and said, "No, they emit radiation, and I'm going to name it after me."
Yeah. So he's trying to disprove an individual. I'll have to look it up a little bit more, but at any rate, um, what is how does that all play in to all of this?
So you have that, you have the holographic principle. Basically, information content scales with the area and not the volume. The universe basically
Con-
behaves like an
Content
encoded.
scales with the area, not the volume.
Right.
Okay, I'm trying to dissect that. Scales with the area, not with the volume.
So width and not depth, maybe,
Okay.
if you're looking at it in a 3D sense.
Okay. So it expands out, but it doesn't go up and down.
Correct.
All right.
Which is the opposite of the James Webb Telescope because it thinks that it can see deeper than the area wide. So I don't know.
Huh.
So the universe basically behaves like an encoded boundary system. Gravity emerges from behavior rather than the behavior of states like microscopic states. Again, goes into string theory. So
Yeah, so that's my problem with all of this stuff. It's relying on stuff that let me see, string theory.
saying that geometry is basically thermodynamic, which is what Bekenstein was trying to prove, um, with the black hole entropy.
Yeah. So if we look up, this is one of the things that I always advise humans to do, and that is every time you believe in something, try and disprove it. Try and disprove what you believe. And this is the problem with string theory is sure we haven't 100% said it's bullshit, but it's pretty much there. Like it's on its last leg. There hasn't been anyone. It doesn't mean that nobody will, but there hasn't been anybody who's been able to provide enough evidence to really support it. There hasn't been much to say this is actually correct. And again, if you're using your hypothesis, or if you're using string theory as part of your hypothesis, something that is widely um, referenced in something I'm sorry, something that's not widely referenced, something that is actually kind of looked down upon to a certain degree in the scientific community in 2026 anyways.
Mhm.
If this was the 1980s, we'd probably be like, oh shit, we're still working on string theory, but it's pretty much dead as far as I understand it. And again, my understanding of all of this is pretty minimal.
Yeah. Um, I mean, here's the way I see it.
Yeah.
We assume that space was kind of like the container of reality. This is where everything originates from, and then relativity showed us that space and time are flexible. Um, through gravity. Physics is now exploring the possibility that space time itself may be a consequence of something deeper. So,
Yeah. But when
not
you say,
necess-
go ahead, sorry.
yeah, it's not necessarily a stage, but just the appearance of structure. So, this kind of plays off of, I think, episode 9, where we were talking about structure when particles kind of come together to form structure. So it's the appearance of structure, basically when information gets organized. Um, so that's basically saying that particles, once they organize themselves, that's what builds the structure that makes up space and space time. So it may not be made of actual things, but actual relationships between different particles. And that's, it's kind of the element of string theory, but it doesn't disprove relativity either.
Correct. When you say flexible, what
Mhm.
do you mean by that?
Well, you have different things that change. Say, uh, gravity would be the curvature of space time around a specific mass, right?
Correct.
Yeah. So all of that changes depending on whatever variable is there. If mass changes, then the curvature changes. If there's
Yeah.
different variables that changes, so that makes space time flexible.
Yeah, flexible in the way humans understand flexible. I just wanted to make sure that we're not saying it's flexible and it can change.
Mm-mm.
The curvature of space-time, so it curves and it moves, and if it scales, it curves, but it's still a constant if you really, I mean, because the equation is the same um, whether it's something small or something gigantic, the equation is still the same. W
Hmm.
we do see some things like a black hole that really doesn't abide by that, so we don't know what other forces are acting on it, and we talked about dark energy and dark matter, and those kind of affect the way that we look at relativity, and we have to take those into account when we're looking at gravity. But the math is still the math, so I just want to make sure and clear that up. That I didn't think you were saying that
No, no.
flexible. You can change it however you want. It just space time moves,
Hmm.
light bends, um, based off of how massive an object is.
Correct.
Okay, got it. Got it. So for me, there's a few things that I wanted to point out as we kind of wind down here. General relativity already works extremely well. Um, there's I go back to there's no evidence, no experimental evidence that it like disproves any of this. That space time isn't fundamental.
Correct.
Now, just because there currently isn't any experimental evidence doesn't mean there won't be any. Right now, it's all a hypothesis. It's not an actual theory that we can all get around and say, yeah, this should make sense. As far as we know it collectively, this makes sense. Um, the the assumption of time is also a weird one. So, like we because entropy already kind of proves the time stuff, right? Like it's and Einstein kind of proves how time is relative.
Hmm.
If we take that all the way, if we say this is not fundamental, then we're saying entropy to a certain degree is not fundamental. We're saying, and that is fun, as far as I understand it, anyways. Entropy is fundamental. Um, Again, as far as I understand, I don't know if it's true or not, but that would be a foundation. And I would I would I would believe that space-time and or time in general and entropy are kind of they prove one another, I guess, if that makes sense.
Mm, yeah, I think so. There's, going back to the ER and EPR conjecture.
Mhm.
That's suggesting that entangled particles are connected, just by extremely small geometric structures that basically link space time geometry to quantum information. So it's trying to basically say that they're one and the same, or they can be one and the same, or they have that relativity.
Yeah, but again, I don't know much about this stuff, but when we're talking about and maybe I'm not on the right topic, but even ADS, what was that, anti de Sitter?
Mhm.
If we go back and we look at that, if we go back and look at the cosmological constant, it's it almost, well, that's their theory, right? There's I'm sorry, that's their hypotheses. That's Juan's hypothesis, if I'm not mistaken. Was that Juan?
Yep.
What the fuck was his last name? Juan
Um,
Juan
well,
Maldacena,
yeah,
Maldacena, and Mark Ramstonk are the ones that have presented that, right? ADS, and CFT.
yeah.
Um, cool. So, like this one, if we look at their method, if we look at the again, I've only looked at it a little bit. I haven't looked at it at all. I'm not well versed in their papers, so I'm coming at this almost blind. But I have seen enough kind of counters to their and to talk about how it just doesn't match our universe. And it goes back to what I've been saying, that you can't say it scales, and or you can zoom in, zoom out, and it's the same thing if ADS and the cosmological constant, it doesn't really um, doesn't fit our universe.
Correct. So I have nothing else on this one.
This one, I was reaching on this one.
Oh my gosh. Yeah,
This
that was a good one.
so
Good job
for
on that.
me and my personal knowledge about cosmology and all that stuff. This is the beauty of knowing that you don't know shit.
Mhm.
Don't get stuck in the Dunning Kruger effect. Because I think this is what we see a lot in TikTok scientists and TikTok, the flat earthers for sure. And this is a lot of humans who are like, I know the earth is flat because look at this, it's flat. So therefore I can prove that the earth is flat. Like they don't know what the fuck they're talking about.
Mhm.
But
Mhm.
it's nice to look at stuff, and I think that's the point. A little bit of the point of this podcast is to challenge humans to go beyond what they believe, and so we can understand how it all works and get some more information. 'Cause this one for sure had me reaching. They all have me reaching a little bit and learning new stuff, but this one for sure is like I have no fucking clue. I know Einstein, I
Yeah.
know Einstein relatively well. I know his
Mhm.
work relatively well. Um, and that's my big bias is I don't like to look at other stuff that's not based off of Einstein's work, which is not necessarily a positive thing. It can actually be a negative thing to just have that bias, and I only want to believe what Einstein said.
Mhm.
If you really look at it, it's pretty difficult to deny what Einstein did, just the amount of evidence we have to support it. But it's nice to look at other work that says, not that Einstein's wrong, but there's more to Einstein's work, and maybe it's not the foundation. Obviously, science isn't convinced. There's not conclusive evidence that this is true, but it's more of a hypothesis that maybe space time is a consequence of something. Space time is a result of something else, and not the cause of something else.
Correct.
So
And again, this is all theoretical physics. This isn't, I think I said that right in the beginning. So it's not, none of this has been proven yet. I mean, it's still being studied, still being looked at by very old people that are possibly no longer living. So yeah, like Max Planck, he's the father of quantum mechanics. So
yeah, fire hazard. You are late. You are late. I think you missed a lot of us trying to figure this out. You missed a lot of us like not really knowing what we're talking about. So from that perspective, you didn't miss a whole lot, but also just just us trying to figure out this idea that space time is not fundamental, or the potential is not fundamental. Richard is a big believer in the quantum uh, physics world, quantum mechanics world. I appreciate it. I am fascinated by it, but I am one of those humans that needs to see the proof. So I can't get excited about something until we start seeing proof and we start seeing tangible evidence of it.
How are
Uh,
you going to see it? It's microscopic.
yeah, but I mean, it's every. There's a lot of stuff that I can't see, but we can prove it, right? Like again, gravitational waves. We didn't really see them, and we just proved them. We were
Right.
just able to prove them through technology. So there's a lot of stuff that we can't see.
Hey,
Neutrinos.
I work in radio frequencies.
Yeah,
Imagine that.
yeah. Neutrinos is one of the weird ones.
Yeah.
Um, so there's a lot of this stuff where for me it's just like I want to see the tangible evidence, which is unfair. I get it. It's unfair because you have to get to that point. There was a time when Einstein sounded batshit crazy to the entire science world, until he was proven correct over and over and over again. So
Yeah.
I hope we figure this all out in my lifetime. It'd be fascinating. So awesome.
Yeah.
This one was a good one, mostly because they had me reaching. So I don't know how good of an episode it was because we were like, I don't know. We're just talking about humans who are saying things.
Mhm.
Um, I don't know that we added anything to it for sure. But for me personally, like this one was one of these where it had me definitely reaching my point of failure for all of this stuff. So that was a good one. Super duper appreciate that. Appreciate you guys listening. I appreciate you guys tuning in. Richard can be found where?
On Facebook under my name, Richard Fletcher. Also YouTube, although nobody really goes there. I don't post anything. YouTube is under Engineer Reality, and you'll probably just find these podcasts, and that's about it.
Yeah, which is good enough. Which is good enough.
Yeah.
My channel is all over the place. I do some filmmaking work when I do stuff. I do some filmmaking stuff. I'm just getting into repairing technology and phones and all that stuff. So it's a wacky fucking channel, but you could just find me here or also on Facebook, and it's just my name. It's just my name. But I appreciate you guys. I appreciate you guys adding value to the comments. There's been a few shows where a lot of humans have commented, and that helps us out. It helps us learn about other humans that we may not know about, other papers that we may not know about, other hypotheses that we may not know about. So doing that really helps us out. Uh, at any rate, until next Tuesday, uh,
Mhm.
we need to figure out like a catchy signing out. Um,
Hmm.
catchy. You need to add science to your bio. I don't know if this qualifies as me adding science to the bio. Me just talking about science. I might think about it, but we'll see.
Yeah.
But at any rate, we'll see you guys next.